Let's do one more example of finding an inverse function before we start talking about graphs here. So if f of x is 2 minus the fifth root of x plus 3, find f inverse. We just did a power function. This is the opposite of that. We have a radical function that has a fifth root in it. So take it out of function notation. So call it y equals 2 minus the fifth root of x plus 3. I'm going to swap x and y, because that's what the inverse does, reverses the role of x and y, and then solve for y. So first thing, before I handle the radical, I got to get it by itself. So subtract 2 from both sides, and I get x minus 2 is negative fifth root of y plus 3. I'm going to get that negative out of the way, so I'm going to multiply or divide everything by negative 1, which will change both signs on the left-hand side there. We get negative x plus 2 is the fifth root of y plus 3, and nothing wrong with that, but I would prefer to write negative x plus 2 as 2 minus x. So we get 2 minus x is the fifth root of y plus 3. And then to get rid of the fifth root, I do the opposite. I do the fifth power to both sides. So on the left-hand side, I'm going to get 2 minus x to the fifth. On the right-hand side, if I take the fifth root, raise it to the fifth power, those cancel, and I'm left with the y plus 3. And then I just subtract 3 from both sides, and I have that my inverse is 2 minus x to the fifth minus 3. And if I want to put it in function notation, f to the power negative 1, f inverse of x, is 2 minus x to the fifth minus 3. Okay, let's talk about the graphs now. So think about, what do we do when we make a graph? Well, the most basic way is we plot a bunch of points. The graph is a picture of all the points that satisfy the equation, or at least all the ones that fit in whatever window we choose to use. So that we don't mix up x's and y's, that gets confusing sometimes. I used other letters here, but say you got all these points a, b, 2, 5, 7, 9, whatever the coordinates are. You have these points a, b, where f of a is equal to b. By definition, the inverse function is going to be the points BA, where f of a equals b. Or in other words, I take my points from my original function and I literally swap the x's and y's. It's probably easier to do this for graphs because you can point-wise, actually swap the x's and y's. We don't have to do any algebra and solve an equation if we're just trying to take points on the graph of f to find points on the graph of f inverse. A result of this, if you're reversing your x's and your y's, you'll wind up getting that your graph is the reflection across the line y equals x. Here's a picture. This function, the one in red, and this shows something else important too, the one in red is actually x squared, but only the positive side for x greater than or equal to 0. X squared is not 1 to 1. Okay? If we drew the entire function, it would fail the horizontal line test. 1 and negative 1 go to the same y value. 2 and negative 2 both go to 4, the same y value. If I were to graph the inverse of the entire thing, I would also have a part down at the bottom, and the result would fail the vertical line test. It wouldn't be a function. But I can take my function that is not 1 to 1 and make it 1 to 1 by restricting the domain. So we can do that sometimes. If we have a function that's not 1 to 1 on its entire domain, but we want to work with an inverse, we can restrict it to a certain part of its domain. That's extremely useful here. The green graph is the square root of x. X squared has an inverse. It's the square root of x if we only talk about positive values. Right? So anyway, that's a more general discussion there on domain and making it 1 to 1. But if you look at the result of the picture here, in yellow I've graphed the line y equals x here right through the middle. The straight line through the middle is y equals x. And the one that goes from 0, 0 to 2, 4 there, the half of the parabola, that's x squared. And then for positive values, and then we have the positive square root of x would be the green one, it's its inverse. And you see, if you take a point like say 2, 4 and you send it to 4, 2, what you're going to get is that basically y equals x acts like a mirror. It's the perpendicular bisector of my line here between 2, 4 and 4, 2. Every point goes exactly to the point that's the same distance on the other side of that line. Okay? If I made a perpendicular line and went the same distance. So that happens for every point, we get the mirror image. So that's a nice way to do a visual check if you have a square viewing screen to check. Remember, on your calculator you might have to do zoom square to see that feature. So an example, graph y equals x cubed plus 1 by making a table of values, then graph its inverse function. We have already talked about transformations. You could think if you were to graph this, you're going to get x cubed, which has that certain propeller kind of shape, and then the plus 1 is going to move it up 1. But we can generate that by making a table of values as well. I like to do negative 2 to 2 for basic functions. So you plug your values in, negative 2 cubed is negative 8, plus 1 is negative 7, and you can check and fill out the other points I have in the table. plot each of those, and we get the, as I say, kind of the propeller shape, but with moved up. It goes through 0, 1 instead of 0, 0. And you fill it in, and there's x cubed plus 1. If I were to graph the inverse, it should be the reflection across the line y equals x, and the easiest way to do that is to take my points that I used to draw the graph of, I'm calling it f, here we called it y, but whatever the function is, for my original function, take its points and swap all of the x's and y's. We can actually do that for our entire table. Take what were the y values and make those the x values, and what were the x values for my original function, make those the y values for the inverse. And if we've called it y instead of f, sometimes we do use the notation y to the negative 1 for y inverse. And that's all you have to do to come up with a nice graph. I take my blue points, my 5 points that I started with for x cubed plus 1. I don't even have to find the formula for the inverse. I just swap the x's and y's on all those points, plot those, and then fill it in with the nice smooth curve, and we have the inverse. And I added here with PowerPoint a line through y equals x. You can see we have the mirror image property there. And let me just add, I didn't ask it on this question because it's not as informative maybe for this particular example, but I also like to point out you're swapping, when you do inverses, you're swapping x and y, you're swapping the domain and range. If you find the domain and range of a function, the inverse will have exactly the opposite domain and range. For this example that we see on the screen right now, it's negative infinity to infinity for both. X cubed plus 1 is what we call a polynomial. I can do x cubed plus 1 to any values. I'm not dividing, won't divide by 0, won't take square roots of negative numbers or anything. So the domain's all real numbers. If we kept making the window go out larger and larger, it goes all the way out in all directions. The range is also all real numbers. Okay? And same thing for its inverse. The domain is all real numbers, the range is all real numbers. If we back up to my previous example I showed with x squared and the square root there, so by restricting it, my red graph has a domain of 0 to infinity. Let's say it's going off to infinity. So my domain is 0 to infinity. The range of my green graph is 0 to infinity. The range, I guess this one again is not quite as informative because the domain and range are the same. They're 0 to infinity for each one, but they're being swapped in examples. Here, since neither of those examples worked very good because the domain and range were the same on both of those functions, here's one. This is actually x squared plus 1, and I chopped it off, did the piecewise to make it positive here. But so if you look at this function, x squared plus 1, its domain is 0 to infinity, its range is 1 to infinity. For the inverse, its domain is 1 to infinity, its range is 0 to infinity.